what is the dependency chain of these operations? Can I break it down? Can I expose some inherent parallelism or whatever? Try to write in a different way, okay, your code, and see what is the effect. Okay, so some C-specific hints, because, I mean, know your tools, for instance, okay, is one of the first factor of optimization. And you have to be aware that storage classes have consequences, okay? There are global variables, local variables, or registers that, I mean, they are optimized or can be optimized by the compiler in a very different way. And qualifiers are important. For instance, how many of you know C, the C language? Some of you, more or less. How many of you use restrict? Or even know about restrict? No clue. Well, this is fundamental. This is why there are people around the world that write articles about the fact that Fortran is so much more performant than C in scientific calculations. No? I hate Fortran. No, it's a joke. Why is it so? You see, I mean, it's running on the same CPU. It's something inherent in C that is more stupid. You cannot do an addition better than Fortran. Why in the hell? No. The point is this one, actually. No? So Fortran has let's say, very great management of memory, no? Inherently, but there, Fortran 90, whatever it is, but okay. So pointers is something not natural in Fortran, actually. So actually, C is basically based on pointers, no? So I'm going to Blackboard. I'm sorry for people that will watch the in case the registration. But so, what if I have some my function, okay, that have this kind of imprint? So A, well, let's go there. Okay, no, A, and then again double and B, okay, for instance. And then we do something, for instance, okay, even there is a C, okay, and then you have CI equal AI plus BI, something like that, okay? There are articles on the web that tells you that in Fortran this is much faster than in C. Why? Because the C compiler is not guaranteed, because the C compiler is extremely good, but is as good as you permit, okay? Here, there is no guarantee in any sense that A, B, and C will never overlap. These are just pointers. The compiler, at compile time, absolutely has any way to know where those pointers will point to. Or if the memory regions they point to will overlap as the index I just run. Okay? No way. So it must be conservative. But however, what if you tell him, no, trust me. I know what I'm doing. Those memory regions will never overlap. And A, B, and C, while offsetted, indexed, or dereferenced, as you want to say, will never point to the same memory region. Then the C compiler can act differently and operate a lot of more optimizations. This is what restrict is. If you put here a restrict, you're telling this to your C compiler, and then you will see that this is faster than hell and as fast as Fortran, if not even more. Okay. I'm joking about Fortran, of course, but this is the point. All the article about the fact that Fortran is much faster than C, blah, 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 are written by people that do not know the C. It's more complicated. I mean, my personal opinion, C++ is fantastic for very complex code and design, high-level design, blah, blah, blah. but it's very difficult to be used effectively for high performance computing because he has a lot of overhead. And the point is that that overhead, you don't know exactly how it is because it's, behind the implementation of the C++ standard that is up to the engineers that have written the compiler. So you don't know. I mean, there are clear examples. For instance, a couple of years ago with Alberto, the guy that you knew the 2 days before, he had a strange problem with C++, whatever. He written something in a way, and it worked in another way that in the C++, accordingly to the C++ standard, was the same, functioning the same. The performance was much worse. No? And we discovered that it was because in that implementation and overhead, blah, 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 and the second way was much worse. Okay, and so C++ has this disadvantage. You must be really a great master of C++ to have to write high performance. It's in my opinion, it's more difficult in C++ than in C. Okay, there are very few things that you can do in C++ that you cannot do in C actually, even overloading, but it's kind of Jedi level of C. Okay, but however, still, the point is that again, know your tool. Okay, so just learn about the restrict or volatile. Okay, and your code will have a great advantage. Okay, and sorry, I didn't remember that there was a slide about the restrict. Okay, this is exactly what I've said before. Okay, but now you have that on the slide. And this was actually there was here a comment about C++ actually. I just dropped it just not to be too complicated, but whatever. And this one, for instance, so read the fucking manual of your compiler. Don't think that the compiler is just blah, 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 minus O, whatever it is. Compilers are big beasts, okay? And people that compile the compilers are very clever. So read the fucking manual, okay? Because it's important. It's your tool, okay? So know how your tool behaves and what your tool can do in different conditions, okay? For instance, you can actually optimize differently inside your code. For instance, for some reason you may want to optimize differently different piece of code. You can do that. And try to understand, to read in the manual what different optimization level means actually in practice. So what are the algorithms that are in the optimization level, and what are the algorithms that are outside the optimization level, even the maximum one, okay? And use the profile-guided optimization, okay? This is for GCC, but also the Intel compiler or the PGI compiler has this kind of stuff. So you can instruct the compiler to generate some statistical data, basically. So the compiler instruments your code so that you collect information about what is happening during the execution. Okay, and when you execute the executable, okay, then these information are collected and written in a file, and then you can recompile using that file so that the compiler can understand what is happening in the real world when your code executes, and so it can rearrange a lot of stuff in a much better way because it collects information, it uses information that at the compile time otherwise wouldn't be on the desk, okay? Yeah.
For example, before you made an example of the random data
Mm-hmm.
which you were running the code compared with predictable
Yeah.
this kind of approach would be able to discern between
Not with the random.
no, but to apply the optimization statistically based on the kind of
Well, if the data, yeah, in fact,
the same
yeah, good point. In fact, the next statement would have been run your code under different, with the different data set that are of typical use. That is important. So if there is a pattern in your data set, I mean, the compiler can catch it out and use it to reorganize. I mean, if you look in the assembler, you will see that the compiler even replicate your code, depending if it's able to learn patterns in your data, it can replicate your code and, I mean, reshuffle your conditions and blah, 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 so that everything is correct, but based on this kind of data, it can distinguish pattern and be much more efficient, okay? That's damn important. And it's so damn important that you have a specific profiling for branch conditions, okay, which is called the arts, or in general, this is more general, okay, generate the profile and then you can reuse it, okay. Normally you have a great improvement in performance. I mean, it can be, I mean, sometimes even 50% or even more, okay. So just try and see what happens to your code. Okay, this is just pictorial view, the winding road of optimization. You start from your design, you debug, okay, of course, and then you profile your first implementation, which is the topic of the next half an hour. And profiling means to spot where there are the computation-intensive lines, data-intensive lines, and where is the resource stalls, okay? And if you are lucky, you have this kind of profile. So there is one spot that is taking all the stalling or computations or whatever, if you're lucky, but you will never, you never are. If you, I mean, kind of, you are just few spots, okay? And what normally happens is that it's totally flat. Okay, so that the troubles are all around your code. It is, of course, a normal condition. And then you optimize the memory. So where are bottlenecks in memory access? You trace the hot data in the and hot and cold field in the structures. You have to take care of the I/O. Then you start to vectorize. Once you have understood what happens, you try to vectorize your code explicitly. Then if you are parallel or multi-threading in any case, you try to understand how your workload behaves. But I mean, this is for tomorrow and the day after. Parallel issues, okay, and then validation and verification, of course. And I mean, there are loops inside here because, of course, the debug is everywhere, okay, as usual. Bugs are everywhere. You are still in need of profiling when you change your memory pattern or you vectorize and whatever. So there are loops inside this, this winding road, okay. Well, now profiling. So as first you should, I mean, in principle, if you are the author of the code or the co-author of the code, you know what the code is doing, more or less, sometimes, okay? But it may be also that you are, I mean, joining an effort, for instance, a project, or that you download a code and, I mean, it is 50,000 lines, no? It takes time to read code, blah, blah. So one of the first things that you can do is to get a map, no, of your code. And absolutely the first one and the most basic one is the call graph, which is basically a control flow graph, no, that exhibits the calling relationships among the different routines in your code. So who is called by who, how many times, no, and how many cycles or time is spent in different part of the code, okay? And you can have static call graphs, which means that a program just analyzes the source of your code and understand the relations, okay? Which is, in any case, a good point because you understand how the code is designed. But actually, what tells you most is the dynamic call graph. So how the code behaves when it's running, actually. So where it spends most of the time. Okay, and the most complete graph is context sensitive, so which means that every call stack of a procedure is recorded as a separate node. So it depends. I mean, I can, if I am a routine and every one of you is calling me, I mean, you may call me just once and you 1 billion times. It's different. So the call count is 1,000,000,001. Fine, okay. I'm quite intensive guy, but it's different, okay. So it is important. Well, so basic profiling concept. So you can, how can you profile a code? Well, one thing that you can do is to instrument the code. So you insert extra code, probably not you, but some automatic tool, okay? You insert extra code at compile time. So roping function calls. We can even write your own routine in, for instance, in Python or whatever it is, a grep routine, whatever. So at every function call, you rope it, and you add some kind of general counters, for instance, something quite easy to do. And you sample, otherwise you use sample. So what it does mean? That you stop once in a while your CPU, and you see where the program counter is. So where the registers that the register that contains the pointer to the next instruction is. Okay, so you get the exact point at which the program is in that moment, and then in what function it is, and you increase the counter on the function and the counter of that line, for instance, in the source code, if you have enough information to do that. So this is sampling. N times per second. So 1,000 times, 100 times, whatever it is. And then you have the debugging, and it is when you enter in bi-step execution mode, which is a specific mode of execution for the CPU. Well, this is basically the same stuff that I told you before in pictorial view, and you can collect the program events, or you can do periodic sample. Okay, so this is something quite useful. There are instruments, for instance, Valgrind, that we will use, okay, in the afternoon, and that basically create a sandbox in which it simulates the run of your program. So you can really have a very tiny profiling of what is happening line by line. Okay, for instance, it is much slower. It takes 1,000 times more to execute, of course. So it's impractical if, I mean, you have a very large data set or whatever it is, but still quite very, very, very useful. Okay. Well, what can you use to obtain the call tree, for instance? Well, you can use GCC and gprof. You can use the Google perf tools. You can use Valgrind. You can use perf. Or there are a lot of others, but mostly non-free tools. Okay. Well, there are a lot of very good tools outside there, but still there are a lot of very good tools that are open source, actually. Okay. So it is important to, yeah, anybody can run a linear tools that actually cost 100,000 €100,000 per 64 cores. Okay, we cannot afford, for instance, my institute to pay 150,000 euros per year. Okay, now we have access to this because we are in a project in which the ARM is a partner, so we have this. In few years, I mean, the project is done, and we don't have access to this fantastic tool. It is fantastic, but, well, it costs a lot. So just learn how to use open source tools that are most often as much fantastic as private tools are.
On the previous slide,
Yeah.
you told us that instruction set simulation.
Yeah.
It means that you must have a good and well set up model of how the real CPU
Yeah.
performs that code.
Yeah.
How is it possible when, for example, Intel doesn't give you these low-level details
Well,
to simulate?
you have enough details, or you can do as Valgrind do. So you build up a sandbox basically, and yeah, you may lose some accuracy actually. Yeah, it's just one of the way in which you can profile a code. Okay. Valgrind actually is very interesting because it creates this sandbox. It doesn't simulate the instruction set. Okay, it actually deliver it to the CPU, but it can simulate, for instance, a cache, or no. That's quite interesting. So, but we'll see that in the.
It's not so easy in any case to replicate.
No, it's not easy.
The real.
No, it's not easy. No, absolutely. In fact, when you profile a code, you also interfere with the code, of course. If you instrument the code, that's obvious. But even if you sample, you have to take care in interpreting the results. But still, that profiling is quite useful. And how many of you have ever used one of these tools? No one. Okay. Well, so the most simple, the simplest code is gprof, which is something that is basically embedded in the new compiler. By the way, new compiler is not the compiler of the poor people. It's one of the best compiler around there. Okay, just to be clear. Don't think the Intel compiler is for sure much better than a GCC. Actually, there are many cases in which the Intel compiler has taken the source code of the Intel compiler, or cases in which the Intel compiler is taken from sources of the new compiler, or cases in which the new compiler compile much better code than in the Intel compiler. So GCC is a very good C compiler. So it has gprof, and you activate this by using -pg option, okay? And you should also profile turning on the optimization you're interested in, because you want to profile exactly that code, not an unoptimized code, okay? You want to profile exactly that code. And so you turn on the optimization, -pg, -o, whatever it is, okay? Don't use the option -p. It's an old option, still there. Use -pg. And then you run your program normally, okay? And profiling infos will be written in a file named gmon.out, okay? And then you can read these informations by using gprof. And gprof will tell you a lot of stuff. You can visualize the call graph, read the man page, of course. So just using, this is a Python utility, you can search and download it. And the dot, probably you know, it's a utility by which you can draw basically graph, okay? And you have your call graph, okay? Well, now that we encounter gprof, we can say goodbye, because it's a very old dinosaurs. I really love gprof. It's my first choice for a quick and dirty job, okay, because you just compile, blah, 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 execute, you have your call tree. The call tree is correct, of course, it's just not a matter of being old or not. And you have an assessment of where the time is spent. Very good, perfect. I'm still using it and so on, very simple and very effective. However, for instance, it lacks real line-by-line capability. It can just track functions. But, I can have a function that is hundreds of lines or thousands of lines. Shouldn't be the case, okay, because remember, just a small file, blah, blah, blah. But, okay, in real world it is, okay. And so, gprof cannot track line by line, cannot provide shared libraries, it lacks real multi-thread support. So it's an old guy, and we have to respect him, but also just to use something more modern, okay? And it can easily lie, okay? So consider this code, okay? There is actually a loop which does nothing, okay? This volatile here, I mean, if I write this one without a volatile, okay, the compiler will recognize that I'm cheating, okay, and it will basically drop this out, okay, because it's not stupid. It recognizes it is a loop that is doing nothing, okay. But if I put the volatile, this volatile means don't worry about that because this memory location, a variable is a memory location, can or will be read by someone in the universe that you don't know about, okay? And so the compiler doesn't optimize because, I mean, okay, I know. So probably, someone just want to read the value of this I while it's running, who knows? So, okay, so it does not optimize. And in this case, the purpose is just to be able to perform this stupid test, okay? And then you have this I'm sorry, this of course is an error. You have these two different functions. It's the same function but with different name, okay? It just calls loop with an argument n. So here you execute loop for what is 100,000 times, and here for what is 1 billion times, whatever it is, okay? Very stupid. So what you have, this is the flat profile that gprof gives you, is the loop is, called, this is called, okay, 2 times, fine. One from heavy and one from light, okay. It takes about, dot seconds, 100% of time, and you then cannot see any difference. Look, come on, they say, no. Here, most of the time must be spent from the heavy, not from light, of course. No? But you cannot see this from the GDB profile. Why? Actually, read the fucking manual again, okay? Because in the gprof manual, it's clearly written, okay? We assume that the time for each execution of a function can be expressed by the torch time for the function divided by the numbers of times the function is called, right? So thus, the time propagated along the call graph arcs to the function's parent is directly proportional to the number of times that the arc is traversed. It says, I'm not complex enough to understand different patterns. So my count is 1,000,000,001. I know that I've been called from 2 guys, so half and half, okay? So know your tool. But then you get a wrong profile, okay? But it is not the fault of gprof. It's just an old guy, okay? If you use Valgrind instead, well, you have actually that this is the fraction of time spent in different arcs. So one calls from light, nothing, and one calls from heavy, basically all. So Valgrind is a different type of profiler, okay? So different tools. Then we'll see how to use it in the afternoon. Well, the call tree, well, we can use, but probably better that I tell you this in the afternoon, and also perf. Yeah, I will move this in the afternoon. Yes. So how much time do we have left? 25 minutes. So do you have any question about what I've said before, about optimization, CPUs, or whatever, something that is absolutely not clear, something that you don't know, so much better to start from scratch?
I just wanted to know the profilers. There are some profilers that are with GUI, which are installed on default on some system. I know there's one on Linux mainly. I know that there's instruments on Mac. Are they good? Do you recommend it? Do you know of them?
I don't know about the Mac, but do you know, Stefano? You are the.
Actually, as a profiler, includes that if you optimize with care all the memory hierarchy that Luca mentioned, then the optimization that you put there can be maybe exploited the same way on a different machine just because caches are different sizes and so on and so forth. So the point is, in any case, any tools that you have is very good to take a look and to profile your code and to understand which are the bottleneck and the hotspot where you have to work on. Then remember that there is no single solution that can be ported across all the computational platform that you are using as a computational scientist. But in any case, again, tools, any kind of tools that allow you to understand exactly what your code is doing, even if this, what is doing and what can be optimized is very specific to the platform, to give you further hints and further idea how to go for a general approach.
Thank you.
Well, on Linux there are a lot of native tools, and I think that 99.99% of the HPC facilities run Linux, basically. And you have, so basic and system tools are these ones. I mean, Valgrind, and can be, you can install it in your home if it's not system-wide. And so you have, yeah, gprof, GDB, but also perf and the gperf tools. Perf is a very fundamental utility in Linux. I'll give you some instruction in the afternoon. With perf, you can profile your code at line level, and you can also access to the performance counters. Okay, that is something that we'll see in the afternoon. Performance counters are basically some hardware counters that are in your CPU that count events. No? There are a lot of possible events. For instance, a cache miss, it's an event, and a performance counter is increased. So you can know exactly how many cache miss are occurred in a given time lapse, because then you measure the difference. Now it's an increasing counter, so you measure the difference, of course, from a start point and an end point. Okay, and you have how many summation, how many floating point operation in single, double, vector, how many branch miss, how many memory access, L1, L2, L3 access, whatever it is. No, it's very precious amount of information. For instance, this one, I mean, you know, before when I shown you how many branch miss or cycle per instruction, blah, blah, it was obtained with perf, okay, for instance. And to access this hardware counter, you can use this perf. PAPI is a library, okay, that I'll show you in the afternoon. Intel MPI in Liquid also, and I think that Stefano has something on Liquid, some quite quick and dirty. And then, but here we are in the realm of parallel computing. You have a lot of very complex, very good toolboxes like HPC Toolkit, Open SpeedShop, Tau, Scorpy, and so on. I've just mentioned in this. Okay, so of course we don't have time to go in detail, but just so you have a map, you can just start to search and read and understand how they are very complex code, and they are totally free. Okay, then you have vendor tools. Okay, this one is very good, but it's quite expensive, for instance. No, but I mean, if you really understand how to use this, I will say that you don't need this. This one is, I mean, really precious because it's also a debugger, a parallel debugger, okay, which is very difficult to have. I mean, there are no open source free parallel debugger that really work, and that's, I mean, that's a problem actually. So something on the debugging, and then we jump in the afternoon for details about how to use the profiling and debugging tools with hands-on exercise. So this is the outer and the right, so an introduction, what it means to debug a code, and how to inspect a code crash, and how to debug a running process actually. So, okay, that's just a joke, okay, so there are more insect species than have not been described. It means that there are a lot of bugs that you don't even know about in your code, okay, but that's true. And if you have one bug every 1,000 lines, you are a great programmer, okay? very great programming. One bug every 1,000 lines, it's wonderful, okay? Unbelievable even. And so, just, I mean, to end the morning with some relax, how it comes that they use the bug, okay? Everybody knows the story about the animal in the multivac, blah, blah, blah. But it seems that it's more ancient. So the usage of bug and then the bagging is a long-standing tradition. No? Actually, the story happened in 1945, and Grace Hopper is reported to have written in its diary, and I found this page, about that as first actual case of bug being found, actual case of bug. But actually, Thomas Edison, many years before, found another actual bug in one of these phones, it seems, causing some problems. So he was already talking about bug and debugging, okay? But actually, I mean, the immortal Asimov used this in 1944, so 1 year before the Mark II accident, okay, in one of his popular stories. But okay, this was just funny infos. You can track them in this article. So, what is true is what is written in the letter of Thomas Edison, actually. So, months of intense watching, study, and labor are required to face the bugs. Okay, that is damn true. It seems that from statistics, about 60 to 70% of the time in a life cycle of a code is spent in debugging. Okay, so it's a serious affair. It's not just some joke. Okay, so so what is the best way to proceed? Okay, that is, well, then, of course, I mean, don't lie, everybody do that, okay? Don't lie, okay? So, I'm still doing this, okay? Print. Okay, it's effective, okay? Sometimes it's actually effective, so why not to do that? However, the point is that, for instance, I mean, it's too chaotic, of course, in itself. You cannot have megabytes and megabytes of print that you get, and you get lost just trying to read them. But the point is that also, in many cases, you have the print, you have a segmentation fault, or not, whatever. You have the print, and the problem disappears. I mean, it happens, no? So I think, fucking. That's normally the signature of a memory problem, the pointer problem, okay? But point is that when, I mean, the compiler compiles, I mean, something changed in your code, some positions, okay, in memory, and then the problem changes, okay? That doesn't happen anymore, okay? It's really common, actually. So, or you can use a debugger, of course. Which one of you have ever used a debugger? GDB, for instance. Really? So you're lucky, you don't have bugs. Ah, you have bugs, okay. Damn it, I have. Fine. So, GDB is also a very, 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 very good product. They are linear tools that cost 150,000 euros for 60 cores, is based on GDB. As a parallel debugger, it actually calls GDB underneath. Okay, so GDB is damn good, right? So there are 3 basic usages of GDB, and debugging a code, inspect a code crash, and debugging a code which is already running. Okay, because sometimes, all right, normally you are the programmer and you run a code, but sometimes if you are, I don't know where, but for instance, system people or whatever, so there is a code that is buggy but cannot be stopped, for instance, might be, okay? So you can, or you cannot reproduce the, in any other way, the bug conditions. So you run and then you have to attach the debugger at the right point. Okay. You have to compile with the debugging information. Okay, that is fundamental. How to debug a code. You have to produce to tell the compiler to insert in the compiler compiled program the debugging information. That means basically that it inserts some strings, reference point, reference, blah blah blah, so that you can track each instruction to the line, the source line that from which it originates. Okay, that's important. Otherwise, you cannot. You debug just machine code, which is unreadable, and so you have different level of debugging. So minus G with a level 1, 2, and 3, and minus G GDB that actually had some specific extended info. Okay, this is for the GCC. You have also the same is for Intel compiler PGI. So minus G and a level is a standard, okay, historically. So it must work with every compiler. So compile, blah, 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 minus G, and you've done, or minus G3. And then you start like this, GDB program, okay. We will try with this code in the afternoon. And then you enter in this kind of interactive session, and you can start to give some command to the debugger. So you have to run the code, of course. You set some arguments. Probably your program wants some input arguments, whatever it is, and then you run. Okay. But the point is that if you run, it runs. Okay, fine. And it may be that you arrive just until the end of the program, but then you don't have a bug that is a segmentation fault or an illegal instruction or whatever it is, but your results are not correct. Okay, so you have to stop the execution at some point so that you can track line by line what happens, and you can print the value of the variables, blah, 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 so you catch exactly the point in which something not correct is happening. And so this instruction is break. Break and the number of the function, it means that it will stop at the entering on the function, or you can break at the location, which means a line number. The line number refers to the source code from which the code that you are debugging has been compiled. Okay. If you change the source code, of course it's not. Use the cross-reference. Okay. Then you run, and it will stop exactly at that break point. But then, I think that this must be seen live. Okay, in the afternoon. Okay. Any question, comment, doubt? I think that we have 5 minutes, 10 minutes. Do you want to go deeper in something? No? Absolutely.
So this is just one for Java application, right? For Java
program. No. Because for interpreted languages, they might have some specific tools, internal tools, no? Python, Java, they have some specific tools. Because, the point of profiling, no, is, told you before, that point is that you're really interfacing with the CPU when you profile, okay? Because what you're doing here, no? Either you instrument that, well, you can profile your Java code because you instrument the code to profile itself, okay? But otherwise, if you sample, actually you will be profiling, you can profile the Java interpreter that execute your Java code. That is what you can do with these kind of tools, but it's not what you want to do. No? So I think that there are native tools that can profile. For Python, there are. I think I'm not an expert of Java. I'm sorry, because it's not HPC. No? So, yeah, I mean that's different. This was really focused to HPC, no? And HPC is not, of course, by interpreted languages. No? So, yeah, you profile, you directly interface with the CPU that is executing a code. No? You are definitely killed. Well, so then we can just move to the afternoon, because yeah, really I think that this kind of stuff is more effective if you have the hands-on. No? Stefano, volevi aggiungere qualcosa tu? Se no abbiamo pensato, boh, insomma. Sì, ho introdotto sia profiling che debugging. Direi di sì. Certo.
Io ho sempre lavorato in Fortran e quindi il C lo conosco
Per sentito dire,
no,
insomma.
sì, no, poi riesco a riconoscere i comandi.
Sì, poi insomma. Sì.
E quindi posso avere difficoltà a seguire il resto oppure...
Perché il concetto è quello, cioè in Fortran funziona uguale.
Poi un'altra cosa, questo magari banale,